coming. So today I'm very pleased to have Jane here. She's from Oxford, and she will talk about coloring, right? The coloring of hypergraph. Please.
So thank you very much for inviting me. I'm really happy to be here in Korea. I will indeed be talking about the semi-strong colorings of hypergraphs. So this is some joint work with your very own Kevin Hendrey, who's here, and he can help me with questions. Freddie Illingworth, who is at UCL, and Nina Kamchev, who's at the University of Zagreb. So this project that I'm going to be talking about, we started in a conference at Barbados over the Easter a few months ago, and that's the first reason why I have this picture here. So this is a bromeliad, some particular plant, which, as far as we know, is native to approximately that area. There's a second reason that it's here, which is that it will actually be important in the proof that I want to be talking about. So in order to prepare for that, I'll give you an inaccurate anatomy of a bromeliad. So this is a sort of kind of how the flower looks. At the top we have this red part. It's called the crown of the bromeliad. And here there are leaves, but we call them petals. So we'll just keep that in mind for later, and you'll see that it shows up. It turns out to be a structure that is very important. Okay, so to start with though, I think I should just introduce hypergraph coloring in general. So the point here is that if we're looking at coloring graphs, the condition to be a proper coloring is very natural, right? We want coloring so that no two adjacent vertices, have the same coloring. And I should mention that all the colors I'm talking about today, well, with one small exception, are vertex colorings in general. The thing is though, when we go up to hypergraphs, now our edges can have more vertices than just two, and it's not actually clear how to generalize this notion of a proper coloring from graph to hypergraphs. There are quite a few choices we have to make. So one definition that's become probably the most prevalent in literature is a weak coloring. That's maybe the one that you'd be most familiar with, where we have no monochromatic edges in our coloring. The second most prevalent is the strong coloring, which is where we want every edge to be rainbow colored. So that means in each edge, no two vertices have the same color. But there are a lot more variants that are studied, and a particular one I want to talk about today is called a semi-strong coloring. I've labeled it 1.5 because in some sense it interpolates between this weak coloring and strong coloring. So this is the main definition. A coloring of the vertices of a hypergraph H is C strong, so I'm adding parameter C here, if every edge E sees at least the minimum of C and the size of E distinct colors. So the point here is, if it's C strong, I want every edge to see C colors, but maybe some edges are too small, that's fine. I just want them to try their best and have all different colors in that case. Okay, so here's a quick example. I have a graph here. In this first coloring, I noticed that in each edge, I indeed have no monochromatic edges, so I do have different colors. So this is a weak coloring. And I can also say that it's too strong because I have two different colors in each edge as well. And in fact, the notion of weak coloring is just exactly too strong coloring. If I look at this one, all of my edges are now rainbow, so this is a strong coloring. It's also a 3 strong coloring, but it's also, I guess, a 4 strong coloring or a 5 strong coloring. So we can kind of think of strong coloring as being equivalent to infinity strong, or really just take K strong, where K is bigger than the size of your biggest edge. Okay, so in that sense, this notion of C-strong coloring really generalizes both weak and strong colorings, and it's extremely naturally thought. And as usual, when we have a notion of coloring, we have a notion of a chromatic number, and here we use chi HC to denote the smallest number of colors needed in the C-strong coloring of this hypergraph H. So this is something that we thought was extremely natural, but surprisingly, we really struggled to find any references to it in literature, apart from the problem we were studying. The earliest that we could find were just from something like 2006, 2007, where there are a couple of papers studying generalized chromatic polynomials, and that happens to generalize naturally to a sort of C-strong case. But apart from that, the main line of work on this seems to really be on intersecting hypergraphs, which is the next thing I'm going to define. So I'll keep this definition of this chromatic number on top and define a hypergraph H to be T intersecting if any two edges have intersection size at least T. So the at least here is important. That means if I'm t intersecting, I'm also t minus 1 intersecting, or t prime intersecting for any t prime at most t. And that's something I'll come back to. Okay. So in the context of coloring, this is the main problem that was defined. So in 2012, Blais, Weinstein and Yoshida kind of put these things together and defined a parameter chi tc, which is the minimum number of colors that suffice to C-strong color any t-intersecting hypergraph. So it's not clear that this should be finite at all. So if it's unbounded, we'll just write chi tc equals infinity. And then there's an actual question here. So determine chi tc for t and c at least 0, let's say. So yeah, as I mentioned, it's really not clear that this should be finite, but in some sense there's a little bit of a precedent here, which is the following case in c equals 2. So as I mentioned, this is the weak coloring case. This is the colorings that have been most studied for hypergraphs. And here, Erdős and Lovas showed much earlier than these concepts were kind of studied, that we have chi 0,2 equals infinity, chi 1,2 equals 3, and chi t2 equals 2 for all t great, at least 2. So that gives us a complete solution in this weak coloring case. These are actually really easy to show. So when I say they're solved by Erdős and Lovas, what I really mean is, in a very important paper that they came out with in 1975 on 3 chromatic hypergraphs, they sort of mentioned as a side note that these things are true, and I've translated it into the notation above. So the first one just says, this 0 is the intersection number. If we're not requiring any intersection, we're just saying this is any hypergraph. So there are hypergraphs that have arbitrarily high chromatic number, is all this statement is. Second one, chi 1,2 equals 3. So this one's also easy. What I do is I take an edge, let's let it be minimal in containment. I'll color it 1 and 2 inside, and every other vertex will be colored 3 outside. Then, because it's intersecting, I'm going to get 2 colors always. So that's how you prove 3. And you do need 3 because we have just triangles, for instance. And the final one, for chi t2, we can kind of prove this just by a greedy argument. So if you sort of order your vertices, color them red if you can, or blue if you would create a monochromatic red edge. Okay, suppose that there's a problem at some point. That means you're at a vertex where it's contained in an edge that's otherwise red, but also contained in an edge that's otherwise blue. And that's not going to be possible because if your intersection size is at least 2, that means one of the other vertices in your set was colored red and blue, right? So we get a contradiction. So these are really just small observations here about the case. So when Blais, Weinstein, and Yoshida introduced this problem, they also were able to say something about the values. So let me go over the progress of what we know. I'm going to summarize it like this in this table. So basically, I have my C going up. This is more colors. In this direction, we increase the intersection size. And I'm going to fill in the numbers for chi tc in the middle. So 0, 1 are kind of trivial cases. Let's just say we don't need any colors to get no colors, and 1 color to get at least 1 color per edge. The next thing is, so the observations we saw before fill out this row. We have infinity, 3, and then 2 going on forever. And now the first thing that Blais, Weinstein, and Yoshida showed was that chi tc is finite when t is at least c. So I'm using these ticks to just indicate finiteness. And it's unbounded when t is at most c minus 2. So I get these extra infinities above that. I'll say just a tiny bit about how these were shown. So for the finiteness on top, they had these particular bounds. So chi cc is at most root c times e to c. And there's a slightly better bound, so chi 2cc is less than 2c squared. So notice that as we increase the intersection size, we can't actually get any worse in some sense, because we said that a t-intersecting graph is also t minus 1 intersecting. So this is just a subclass of the graphs we're considering here. So as this t gets bigger, things should get easier, and that's kind of what we see reflected above. So this gives a general bound on all of those numbers. It is a probabilistic proof. So basically what they show is that using a random coloring, you can get C-strong colorings that you need for these cases. The numbers are a little bit weird because they use some result on p-biased measures to prove this. Okay. On the other hand, in the unbounded case, what they were able to use is a monotonicity property, which is quite important. It's that chi of t plus 1 c plus 1 is at least chi of tc plus 1. This is also pretty easy to show. So the idea is if you take a hypergraph, t intersecting hypergraph, where its c strong coloring number is this chi tc, then you add a vertex into every single edge, so just one vertex, but it's in all the edges of this hypergraph. Now you have a t plus 1 intersecting hypergraph, and you can show that its c plus 1 strong coloring number is this, one higher. And then you're actually done, because we saw before that if you have chi 0, 2, then you're infinite, so you just extrapolate based on that. Okay, so apart from that, they also had some lower bounds for these numbers. These are just by explicit constructions. So they showed that chi tc in general is at least 2c minus 2. The example for this is to take a uniform hypergraph. So you have 6c minus 1 times t vertices, and you take every edge of size 3 times ct. As the sanity check, you can check that it is actually t intersecting. The 6ct cancels out, and we get the t, so that's good. And that's just sort of a simple counting argument there to show that this is actually a lower bound. There's a slightly different bound though for chi c minus 1c. In that case, what we find that is that it's a little better, it's at least 2c minus 1. And again, the example is quite easy. So here it's a hypergraph with 3c minus 3 vertices, and every edge of size 2c minus 2. So again, you can check that the intersection size is correct at least. Okay, so they had these lower bounds. They were pretty sure the bounds on top are not tight. So what they guessed was that actually maybe these lower bounds are correct. So maybe chi tc should actually be equal to 2c minus 2 in general, except chi c minus 1c should be equal to 2c minus 1. Possible. On this top bound, there was some progress on this. So Alone in 2013 showed that for t large enough, so if you go far enough right, then you do actually get an upper bound of 2c minus 1, which is not quite 2c minus 2, but it's pretty close. So that's some good progress on that, at least for t big enough. And again, this is a probabilistic proof. On the other hand, this case, they weren't even able to show that the number was finite. So this is a question that they left open. They just asked, determine whether chi c minus 1c is finite or not for each c greater than 2. Okay, so since that was posed, a little bit more progress was made. It's still in 2013 though, so it's quite soon after it was asked. So independently, Chung and Colucci and Gy showed that chi 2,3 is finite. So Chung showed that it's at most 21, and then Colucci and Gy showed that it's actually equal to 5. This is tight, it matches the 2c minus 1 bound up here. So we're able to fill in that value there. But actually nothing more was really said about this for 10 years until we picked it up earlier this year. And so what we've now been able to show with Kevin, Freddie, and Nina is that actually chi c minus 1c is indeed finite for all c at most n, or sorry, c in natural numbers. Okay. So throughout this talk, I'm going to be a bit vague about what the actual upper bound is here, and you'll see why that's the case as I show you a little bit of the proof. But my plan basically for the talk is to give you an idea of some of the ingredients of this proof, and basically where this bound is going to come from. And I'll add a bit more discussion and highlight the questions at the end. Okay. So to prepare for the outline of the main proof though, what I'd like to do is basically prove the 2-3 case. I'm going to use a proof that is very similar to what was done by Colucci and Gy, but I'm making it more efficient at the cost of not getting this tight 5 bound. Okay, so I'll do that over here. And the nice thing is that this proof really uses some ingredients that we end up effectively using more general versions of. So let's prove this theorem, which is that chi 2,3 is finite. Okay. So let's start just by taking a two intersecting hypergraph. I'll always call this curly H. Okay, and now there are two assumptions I'm going to make. First one is that I can assume every edge actually has at least 3 vertices. Okay, so the reason for this is just that if we had an edge, say, with 2 vertices, it looks like this. I would just color this one, this 2, and then everything outside 3. Every other edge actually has to intersect it because it's 2 intersecting, so we'd be done, right? So I may as well assume this. On a related note, the second thing I'm going to assume is that no edge contains another edge. Okay, this is also an easy one we can take just because if we have a good 3-strong coloring, if the small edge is 3-strong colored, then so is the big edge. So we sort of didn't really need to worry about it. Okay, so I'll just assume these. And now I'm going to go into 2 cases. So case 1 is where, suppose that every triple of edges has a non-empty common intersection. That really means if I take 3 edges A, B, and C, A intersect B intersect C, this is non-empty. So what I'll do is pick some edge E, which I'll just fix arbitrarily, and consider other edges intersecting it. In fact, all the other edges intersect it. If I have a situation like this where I'm looking at 2 other edges intersecting it, I know that this is non-empty by assumption, right? So I'm going to look at an auxiliary hypergraph, which I'll call H restricted to E. So what this will have is the vertex set is just the vertex set of E itself. And for edges, we're just going to look at the restriction of every edge to E. So let me write this as E prime intersect E for E prime in the edge set of H. Okay. Now, because of our assumption of non-empty common intersection, this H restricted T is actually an intersecting hypergraph, right? If I take any 2 edges here, which is now just going to be this is one and this is the other, I know that they have non-empty common intersection inside E. So this is intersecting. And now I'm kind of going to use induction. So I know that chi 1, 2 equals 3. So I'm going to take a 3 coloring of here such that it's 2 strong. Okay, so this is E. I'm going to color with chi 1, 2 colors inside. This is 2 strong, so now for any edge that intersects it, I know that it has to get 2 colors inside, and I'll just make 1 extra color outside. So color everything outside 4. And then I'm done in this case. Okay, so let me leave this here, and I'll do the other case below. Okay, so now we know that we can find a triple of edges that have empty common intersection. I'm going to choose one such triple. Let's say A, B, C, such that A intersect B intersect C is empty. And also, I'm going to choose it so that they have the smallest possible union. that give us? So, if I kind of draw this picture, how it looks right now is like this. I have my edge A, B, and C. And it splits up the vertices of, oh, this is H, sorry. Splits up the vertices of H into these sort of regions that we see in the Venn diagram, right? So I'm going to define a coloring based on these regions now, where for every region, I'm going to arbitrarily split it into 2. I don't really care about the middle because I know it's empty by assumption. And I'm going to assign a different color to each region. So color 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and the outside as well, maybe I'll give 13, 14. Okay. It's possible, however, that the regions might have been small. They maybe only had one vertex, in which case I can't really do this, but that's okay. If there's only one vertex, just give it one color. It's fine. Okay, so now I want to analyze, what does a bad edge look like? And by bad, I always mean an edge that doesn't have enough colors. So in this case, does not have 3 colors. Okay, so if I draw my picture again here with A, B, C, and this is empty, the first thing I know is that my bad edge, it can see at most 2 colors, right? So it can only touch at most 2 regions, right? Because from every region it touches, it has to pick up a new color. Okay. On the other hand, it has to also see at least 2 regions, because if it's only in one region, then it's actually contained in another edge, and we said that we were going to assume that's not the case. So let's call the bad edge E. We can write E touches 2 regions only. Okay. So which regions can they be in?
It could be on the outside though, or?
You can't be only on the outside at least, because you have to also be intersecting these edges, just because it's intersecting hypergraph. Yeah, so that's a good point. Of these 2 regions, you can't really have one out and one in, because then you'd be contained inside an edge. Okay, so what else can't we have? You can't have 2 regions only in these 3, because if you're in 2 of those, then you should really be in the middle, but that's empty, right? So you can't have that either. So you have to touch at least one of these A only, B only, or C only regions. So I'm just going to say it's an A.
Can you repeat that?
Yeah.
So it's some when you have a, so here we are assuming that every pair of edges have and it's 2 intersecting, right?
It's 2 intersecting. That's right. Yeah.
What happens if we have some elements outside and elements inside?
Yeah. So if you have part of E in here and part of E in here, for example,
yeah,
then your edge is. Oh, okay. I guess it's not contained in A, but it doesn't intersect C, for instance, right? Because you can't be inside here, you're always going to miss one of A, B, and C, and you have to be a 2 intersecting hypergraph. Yeah. Okay. So let me go through the second part again as well. I said we can't be in A intersect B, A intersect C, and B intersect C. We can't be in 2 of those, because then you're in the triple intersection, which again is empty.
You're contained in one of the 3, right? If you're in 2 of the.
Oh yeah, sorry, yeah. Then you're contained in one of the 3. Yeah, thank you.
Oh right.
Yeah, thanks.
But if you intersect, you might have some elements outside, right? So you could intersect.
But I have
B intersection C.
Then you have 3 colors.
Yeah, then you have 3 colors.
Ah.
Yeah, so as soon as you touch more than touch 3 regions, you have 3 colors, so we're done, and it can't
I
be
see.
bad.
I see.
Yeah.
So outside world is colored already.
Yeah,
right?
outside is also colored 13, 14.
Uh-huh.
Yeah. Maybe I didn't need all of these colors, but I've just made them for consistency. Okay, so we've decided we have to have part of E inside A. Where can the other part be? So again, it can't be in B, because then it doesn't intersect C at all. It also can't be in C, because then it doesn't intersect B at all. So it can really only be here. This is E double prime. Right, this is the only way a bad edge can look now. And now I claim that actually, if I look at E intersect B, E union B union C, then this is a smaller triple which still has empty intersection. Right? So to see that, I just need to show that I missed some vertex here, but I know that, so E prime, this E intersect A is 2 intersecting, so there are at least 2 vertices inside here. They have to be the same color because E sees only 2 colors. So that means there have to be at least 3 vertices in A in total. There has to be something outside. So this is why we split the regions into 2, to make sure we get something smaller. Okay, so that gives me a contradiction, which basically shows that there aren't any bad edges. So this coloring actually does work using, I've used 14 colors.
Why is E intersect B intersect C empty? It's not empty, right?
I mean, yeah.
The intersection.
Yes.
The intersection of E, B, and C is not empty, right?
Oh, yeah. That's a good
When you're minimizing over the triples of number with empty intersection.
Oh yeah, you're right.
E,
So maybe I should
or
use A,
D, E, or
E,
something. A, B, E or something.
and C?
Yeah,
Something like that, yeah.
So,
Sorry about that. There are a few cases to check here.
yeah.
So we have to be a bit careful about things being, about making sure that we actually remove a vertex as well. Okay.
yes.
Let me not dwell on this for too long. We'll make sure it works later. But this is kind of the idea that we want to use. So there are sort of 3 ingredients in this that we want to take out. One is this one here, where we kind of use induction on C, but really what I want to think of it as is induction on the sort of intersection size. I think that's a better way to think of it. The other thing is that the idea of this coloring, so where we split regions and then color by the regions that we obtain, I'm going to kind of call this a regional coloring, but I'll make this precise later. And the last thing is the idea of taking a particular structure out that we want to minimize, and then the way we show that a coloring works in the end is to find a contradiction to the normality, basically. So that's roughly what's going on. Okay. Let me make those tools precise now. So the thing is, an argument like this, though, it doesn't actually work for the general case for like many reasons. One is that the induction here, basically if we're taking this graph H restricted to E, we can kind of only say that this is intersecting. We can't really guarantee that it's like T minus 1 intersecting. Maybe you can do something to fix that, but it doesn't work by itself. The other thing is here, when we're analyzing what bad edges can look like, it really increases in complexity when we have a lot of colors, right, that we can use. So with 2 colors, we can only touch 2 regions, but if you're increasing the number of colors, suddenly you can touch as many regions as you want, and this kind of becomes a problem. So already this case analysis, I'm sort of struggling to make sure it works. You can imagine that, we can fix this up, but if suddenly you have 4 or 5 colors, it just doesn't work out. And in fact, that's kind of intuitive. Like, you wouldn't really expect that just with 3 edges, you can figure everything out for as many colors as you want. So I feel like that's quite natural. Okay, so what we do though is kind of use variants of these tools. So for the colorings, it kind of is just the same as we've done here. So to formalize this, let me define regions more formally. So the idea is for any edges, let's say I have L edges, E1 up to EL, we define regions with respect to these edges as just a set of non-empty intersections. So what's happening is, really, if you sort of look at a Venn diagram, except we can only do that with 3 edges, it's literally the regions that you see, right? So all the possible intersections that you can get. So that means if you have 3 edges here, you can have up to 8 regions, because maybe some of them are empty. That's fine. And a useful thing is that if you have any set of edges at all and look at regions, that actually partitions your vertex set of the hypergraph entirely. Okay. The second thing is that, thinking of it as partitions now, you have a collection of edges that gives you some partition. If you take a subset of those edges, then what you get is that the partition with more edges is sort of a refinement of the one with fewer edges, in the sense that if you sort of look here and use only 2 edges, you get these 1, 2, 3, 4 regions, right? Just using the bottom 2 circles. If you add this top one, then all it does is it splits some of those previous regions up. So you can write the previous regions as a union of those parts of the refinements. So that's something we'll use in a sec. And now we define a regional coloring, which is essentially what we did here. So again, this is with respect to some edges, E1 up to EL. For every small region, so that means you have less than k vertices, we're going to rainbow color them. And for every large region, we're going to split them up arbitrarily into k parts, and then give a new color to every part. So all of the colors we're introducing here are different to each other. So in total, we're using at most k times 2 to the L colors in this. Okay. Finally, so it turns out the k regional colorings, they're really useful, but they're not quite enough for us. So we're going to add a few more colorings in, and the way we combine them is via taking a product coloring. So that just means if we have a bunch of colorings where we assume the colors used are disjoint palettes, then the product coloring just colors each vertex with a tuple of the colors that it got from each individual coloring. And this is quite nice because, so the number of colors here is easy, it's just the product of the number of colors we had originally. The other thing is, if we want to make sure that we see C colors in the product coloring, it kind of just needs to see a total of C colors across all of the individual colorings. That's kind of good. Okay, so the next set of tools is to generalize sort of the second part here, which is to find these special structures. And here's the definition promised, which is where the bromeliad comes in. The special structure that we want, we call a B-bromeliad. It's a sequence of edges, let's say E1 up to EB in H. Each edge is partitioned into 2 parts, PI and CI, where, so CI is, we call the core, PI we consider the petal. And these have the property that the core parts are nested. So C1 is strictly contains C2, is strictly contained in, so on down to CB, and none of them are empty. And we want the petals to be pairwise disjoint to each other and also disjoint to C1. So as a picture, I kind of have this in mind where I have petals here, my cores are nested in the middle, and each edge is, for instance, a petal, P2, together with the core C2. That includes all of this. So I have an extra term, which is the crown, that I kind of pointed out before, this red part of the bromeliad, and it's referring to the middle. So it's actually C1 intersects C2. I think the way this name came about is that if you look at the flower and kind of look downward on it, the middle is kind of nested, and the petals / leaves are sort of disjoint on the side. So that's the picture to have in mind. The other thing we usually do is just assume that P1 is empty, because then it's it actually sort of allows the bromeliad to be uniquely defined by the edges, right? Because now if I have a collection of edges, I take any edge, its core is just the edge intersect E1, whatever's inside, and the petal is everything else. So that's quite nice too. Now the important thing with the crown is that we use that to define a partial order on the bromeliads, because we want to minimize something, and this is it. And what we do is we order by containment of crowns. It's actually kind of easy though. So if this is a bromeliad here, what I'm looking at is this circle. This is the crown. Here's another bromeliad. It's contained inside the crown. So this is actually less than the original black bromeliad. Yeah, so sort of a trick question. We don't really care about this outside one so much. It's really like the comparison of crowns that we want to see. Right, so this circle versus this circle. Okay, so basically the main step in the proof, which is what I want to show today, is how to find a bromeliad, because it's kind of a very specific structure and we can't extract it directly. So to do that, first let me define, if I have two sets A and B, I say that A splits B if the intersection and also B throughout A are non-empty. So these are basically good cases where I split B, so A really cuts into B, or it's also okay if A is contained in B. What we don't want is B contained in A, basically. And
So
then
the crown is C2.
C2.
the crown is,
They're nested, right? So
They're
Oh,
nested
yeah,
in
exactly,
C2.
sure.
Oh, right.
That's right. Yeah, that's exactly right. So instead of finding bromeliads, what we're going to find first as an intermediate structure are k-split degenerate sequences. So we define those as sequences of edges E1 up to EAL, such that each edge EJ intersects at most k regions in among those edges before J. So the regions from E1 up to EJ minus 1. And each EJ has to split every region that it intersects among those. So it might be a little bit mysterious at the moment, but roughly what we want to do now is show that we can build sequences that have these properties, and then we'll show that actually if we have a sequence like this that's really long, we can extract a bromeliad from it. Okay, so let me state that first lemma now. Suppose that chi c prime minus 1 c, sorry, that should be c prime minus 1 c prime is finite for all c prime less than c. So this is kind of an inductive hypothesis here. Now let H be a c minus 1 intersecting hypergraph with chi hc really big. I'll say how big sort of in the proof. Then any c minus 1 split degenerate sequence in H can be extended. Right, so that basically gives us one step of making a long sequence, and then you apply this iteratively to get as long as you want. Okay, so let's show that you can do this. I'm going to keep the definitions here so we can keep track of what's happening. But the point here is we start with a k-regional coloring and just see what happens. So take a C regional coloring of H with respect to these edges E1 to EL that we have so far. What can happen? So there are basically three options. Either an edge under this coloring already sees C colors, in which case, fine, that's that. Otherwise, an edge could see less than C colors, but it splits every region that it intersects of this E1 up to EL. And the third option is that it sees C colors and it doesn't split every region that it intersects. That means it has to contain a region. It can't contain a large region because by definition of our regional coloring, every large region has C different colors, right? So if we're saying at less than C here, then you can only contain a small region. So what I claim is that actually edges of type 2 are really what we want. So for basically the same reason as I said before, if you see less than C colors, then you can only intersect less than C regions. So that gives you the property in K-split, in C minus 1 split degenerate that you want, that you intersect only at most C minus 1 regions. And the splitting property is given directly here. So basically, if I have an edge of this type, then it exactly extends this sequence that I'm looking at. Okay? That means I kind of want to get rid of edges of this type somehow though. So this whole coloring uses only C times 2 to the L colors. So assume my chi is bigger than that first. That means I can't only have edges of this type. So now I want to get rid of things that are like this. So what I'll do for that is define extra colorings that ensure that any edge containing a small region also has enough colors. Okay. So let me do this. This is where we're going to use the induction part. So for each small region S, I'm going to consider the link HS. So the link is actually a pretty standard construction, I think, in hypergraphs. What it is the vertex set, it's an auxiliary hypergraph, is going to be just the vertex set throughout your small region. So I'm assuming this is my small region here. And the edge set consists of edges that originally contained that region, but now, of course, we delete those vertices from the set. So in this graph here, this was my original edge, and now I only have this shaded part, and similarly for the green. Okay, so the thing is, though, my graph was C minus 1 intersecting. I've deleted S vertices from it, so this link is actually C minus S minus 1 intersecting. Right. And now I can take a C minus S strong coloring with chi of C minus S minus 1, C minus S colors. And we know this is finite because that was sort of our inductive assumption here. Okay? And I claim that if I take the product of all of these colorings, so I have a coloring like this for every single small region S, then I'm actually done, basically. So take the product coloring. How many colors have we used? So we have C times 2 to the L here, so we add that factor. We don't know how many small regions there are, but there's at most 2 to the L, certainly, so I'll put a 2 to the L here. And for each of those small regions, I use chi C minus S minus 1, C minus S colors. I don't actually know what S is, but by this monotonicity property that I mentioned way before, the worst thing it can be is just 1. So I take chi C minus 2, C minus 1 here, and that will be fine. So I know that that's finite by assumption. Okay, so now assume my chromatic number that started off very big is actually even bigger than this large number. That guarantees I have a bad edge. And what can that look like? So I've already ignored things here. This is not bad. We already had C in the regional coloring. For any edge that contains a small region, it's now getting C minus S colors from this coloring here, and it has a further S colors from the regional coloring, right? So that actually gets C colors as well. So finally, the only bad colors are actually these middle ones here, which are the ones that we want. So that now gives us an edge to extend our sequence. Okay. So let's keep this lemma in mind for the moment, but I'll try to prove one more lemma as well. So this is basically saying, given we have this long k-split degenerate sequence, we can extract our Bromeliad. So here, let's let H be an intersecting hypergraph. It actually doesn't even matter that it's C minus 1 intersecting, just intersecting will do. Then a long k-split degenerate sequence, let's say FBK long, implies that a subsequence of these edges actually form a B Bromeliad. Okay, and as promised, this is kind of where we see where the bound is coming from. So that will become clear in a second. To prove this, what I'm going to do is define an edge-colored auxiliary hypergraph. So I take a vertex set on these edges that I have, so E1 up to EFBK, in my k-split degenerate sequence. And I make a complete 3 uniform graph out of that. So every triple is an edge. And I promise some colors. So this is what I'll do. If I have I1, I2, and I3 in this order, I'm going to color EI1, EI2, and EI3 green if EI1, symmetric difference EI2 intersect EI3 is non-empty. What that actually means is, so if I take this as EI1, I2, I3, this is just referring to these shaded parts. So if this is empty, then I make it green. If it's non-empty, if this is non-empty, I make it green. If this is empty, I'm going to make it red. Okay, so that defines some sort of coloring. Okay, and now I'm going to use hypergraph Ramsey. So that shows that if FBK is large enough, then I can find a large green or red clique. All right, let's suppose there's a green clique first. What can happen? I'm actually going to show that this case isn't possible. So I want a contradiction here. In that case, I'm going to form an extra auxiliary graph now. This is not actually a hypergraph. It's really just a graph. So suppose the clique is on EJ1 up to EJL. This is going to be KL minus 1, where I label the vertices by EJ1 up to EJL minus 1. So I just popped the last one off. And I promised some colorings again. This time the colors are going to be regions in the edges EJ1 up to EJL minus 1. And how I pick a region is, well, I look at this picture. By assumption, I know that all of these are green, so these are always non-empty. And since they're non-empty, they should contain a region from this partition, which is finer. Right. So this is just a partition right now using literally 3 edges, where it's EJ1, EJ2, EJL. And I colored the edge EJ1, EJ2 by a region of EJ1 up to EJL minus 1 that's contained inside one of these parts. Okay. So the greenness just ensures that such a region exists. Now we use the fact that it's a k-split degenerate sequence, because that means that we use at most k colors. Right? Because if we consider EJL, well, among these regions, it can only actually split k of them. That was the assumption. Okay, but then we can use multicolor Ramsey. So as long as my L here is big enough, I can find a monochromatic triangle. And we just break down what this means. So if I have a monochromatic triangle, for instance in J1, J2, J3, I've assumed, each of these is colored R, that means that this region R is inside EJ1 symmetric difference EJ2, intersect EJ2 symmetric difference EJ3, intersect EJ3 symmetric difference EJ1. But that's just impossible. This is an empty set, because in each of the symmetric differences, we've deleted everything. Okay, so this case is actually impossible. We can't have a green clique. That means we have some red clique. Let's say it's on EA1 up to EAB. And I claim that in this case, we actually get a bromeliad. So as I mentioned, if we kind of assume the P1 is empty, then we basically have the bromeliad uniquely defined already. So we just let the core to be EA1 intersect, EAI intersect EA1. And the petals is just everything else, so EAI throw away EA1. And we can quite easily check that all the parts of the definitions hold. So the core sets are non-empty because it's an intersecting hypergraph. I won't check this properly, but the cores are nested just by expanding this and noting that the set it refers to is this one. And since it's a red clique, we know that this is empty, so that's good. Similarly, the petals are disjoint because this set is empty. And then there are 2 more things to show. So we should show that they're properly nested, which is quite easy to do just by considering regions. And finally, everything's disjoint from C1, but that's clear from the definitions. The C1 is actually equal to EA1. Okay, so the key point here is that we have to have this red clique, and in fact, that just defines a bromeliad for us, basically. Okay, so I have these 2 lemmas now. In total, what it's saying is that I can build long sequences and I can extract a bromeliad. So using those, let me kind of give you the outline of the whole proof in general. So here's the result again. Chi C minus 1C is less than infinity. We proceed by induction on C. So suppose it's true for C prime less than C, and H is some C minus 1 intersecting hypergraph. What I'm going to do is apply those lemmas. So build a long k-split degenerate sequence. I start just with the empty set to apply lemma 1, and I add 1 edge, and then I put it back in with the same numbers and keep adding edges until it's super long. How long? Well, it has to be FBK long, so that I can then use lemma 2 to extract my first bromeliad, B1. Okay, so here's where there's a little bit of hidden information, but I'm saying that now I'm going to take my H and reduce it to some sub-hypergraph H2. The way I do this is I'm going to choose edges that are bad for all the colorings we've tried before. So keep in mind that basically anytime we apply lemma 1, we've secretly tried a bunch of colorings, right? We tried the regional colorings producted with these small region colorings. So we have a lot of structure from this by the time we've been able to choose bromeliad from it. So it's not that hard to choose kind of specific structures that we need here. But I won't tell you exactly what the hidden lemma is here. The other property I want, though, is that chi H2C is very big. And eventually, of course, that's also possible to guarantee. Okay. Now, the reason I want this is so that I can repeat. So now I have H2. I'm going to apply lemma 1, apply lemma 2, extract another bromeliad B2. And again, I reduce to H3 and so on until I have a whole sequence of bromeliads, and the number of them is the same FBK. Okay. And what I've hidden here is I'm actually choosing this H2 in such a way that I can take an edge from each bromeliad, and they will actually form a k-split degenerate sequence as well. Okay, so then I have this sequence of edges, it's FBK long. I do another application of lemma 2 to extract a transverse bromeliad, is what we call it. So it uses an edge from each of the previous bromeliads. And what you can show from that is that actually this bromeliad, if you delete the first edge, it's still a bromeliad. So I call that B star pop because I popped the first edge. B star pop is less than B2 in crown order. Okay, and that's going to give us contradiction because at every step, I'm actually going to make sure that I'm choosing minimal bromeliads. Okay, so what that says is that at the time I chose this, I actually should have chosen B star instead of B2. So this is the final contradiction I'm getting. Okay, so let me make a couple of quick comments on this. The first thing is that actually we don't use the intersection property very much in our proof, which is a little bit surprising. The only place where we needed it actually was that induction step where we kind of went down to this link and made sure we had enough colors. So in fact, we have our general result is something that's a bit stronger. It says this. So if you have non-negative integers, we'll say TLPX with P at least 2, there exists some case such that for any hypergraph H that does not contain a sunflower with P petals and kernel size almost T minus 1. So here's a sunflower where every set is a petal union the kernel, that's common. And the second condition is this link condition that all the links on sets of size T don't have too big L's from chromatic number either. Then we'd also be fine. So basically we can replace this intersecting property with excluding a sunflower, and then all we need really is for these links to have okay strong chromatic number as well. The second thing is that there's a random version of the problem, which is quite interesting to compare the result to. So Alon defined this in 2013. He said, let FTC be the smallest number of colors needed so that a random vertex coloring of any T intersecting hypergraph is C strong with probability, I said 0.1, but any positive probability. Then for the random case, we actually have FC minus 1C is equal to infinity for all C at least 2. That's quite interesting because we've now shown that this chi C minus 1C is less than infinity. So these functions are generally different, and what that's kind of saying is that the colorings we're using are really not random in a sense, and it also shows that the original techniques of Blais, Weinstein, and Yoshida could never have worked on this particular case. Okay. And finally, let me just mention, sort of the big questions here. So now that we know it's finite, what values do we have? That's something that's interesting, or would be interesting to know. So we have 2C minus 1 is at most chi C minus 1C is finite. Our finite is clearly very far from this bound because of our use of hypergraph runs in particular. So I think the best bounds that we have for this might be the Conlon-Fox-Sudakov ones, so something like triply exponential might be possible. But we really didn't try to optimize this because anything we do is going to be far away from 2C minus 1. On the other hand, for the lower bound, we note that for C equals 2 and C equals 3, that should be chi 1, 2 equals 3 here. They actually match the lower bound. So this was the original conjecture of Blais, Weinstein, and Yoshida. Is it actually just equal to 2C minus 1? So that would be very interesting to know. And I'll reiterate the general case as well. So if we have, in general, 2C minus 2 is at most chi TC, which is at most this root C times e to the C, or if T is big enough, it's at most 2C minus 1. So again, question, is chi CC equal to 2C minus 2? This is enough to imply the general case, again, because T intersecting is T minus 1 intersecting. Or maybe the most approachable question here is to ask, if T is big enough, is chi TC actually equal to 2C minus 2, instead of just this 2C minus 1 here? Okay, so I think I'll finish just with that. Thank you very much.
Thank you. Any questions?
So, what do you compute when C is 4? Is it still very hard to compute?
It seems like it's very hard to compute. So even when C is 4, the best bound that's known right now is this one we get from our proof. So it's something very large. And we didn't actually do any explicit computations to get numbers there. Yeah.
Is there some relation between these two open problems? Do you, like, if one is proven, the other can be improved or something like that?
Not that I know of. I think they're pretty independent. It's interesting that this boundary case really seems to be a little bit different to the others. I mean, it's clear that it should. Obviously, the graphs here sort of the graphs here are contained in the collection of graphs we're looking at here. But yeah, we don't seem to get any relationship like that.
Do you have another example of a natural class like T intersecting where your conditions of your main theorem apply?
Not particularly, and actually, so it seems like these conditions are like kind of necessary. We sort of did study what happens with this link. So I guess roughly the way to interpret this is that sort of the problem to the obstruction to having this coloring is really if we have links that require hypergraph numbers, so links that are kind of contained in a lot of edges. That's roughly the structure that's coming out. So what we were able to show was, we were able to do a little bit more on characterizing case, for instance, chi C minus 2C in terms of the links and so on. But that's kind of like the heart of the condition that we need. Yeah, I would say. But yeah, we don't know that this is necessary. Like, I wouldn't go that far. Yeah. It depends how you interpret the condition.
Do you have comments? Or?
I guess, yeah, I mean, in some sense, this condition that the links have bounded chromatic number is necessary.
Yeah.
If you have a link with high chromatic number, then just restricting to this the edges involved in this link, the T plus L chromatic number of this set of these edges is going to be large. If the link has large chromatic number, then the stronger chromatic number of the edges from the original hypergraph is already as large as the chromatic number of the link. So what we could actually, although the chromatic number gets infinite after you take when you look at like the C strong chromatic number of like C minus 2 intersecting, this is infinite. Again, the only reason that it's large is because of these links. So one thing we can actually say is that in that case, if the chromatic number is very large, it's because there is some link whose chromatic number is equally large, and there's really no difference between coloring the worst link and coloring the entire graph. When the C strong chromatic number of a C minus 2 intersecting hypergraph is very large. So really this is the correct obstruction for coloring highly intersecting hypergraphs. Although the exclusion of a sunflower, there's less that we can say. You do need to exclude something, but maybe you could give a more general condition there.
Yeah, I think it's not clear that like you might be able to replace that with something else.
There it is. It's pretty natural to exclude sunflowers from.
Yeah, I think so too. It's also worth noting that, so in this case, the fact that FC1C equals infinity, the counterexample to this is really just by taking the sunflower. So you can imagine just a star. If you have a fixed number of colors R, just look at a star, so that's the C equals 2 case, where one intersecting. You can add as many leaves as you want to this star, and your probability goes down to 0 of having every edge have different colors, right? And that extends for general C by using sunflowers here. So in some sense, it's kind of, sunflowers come out naturally as well. So we're saying that, we know that what we found is not a random coloring, and sunflowers are sort of exactly where that fails. So in that sense, I think it's also natural in the theorem.
Is there some? Does it make sense to consider list coloring version, or
A list coloring version.
maybe you just
Ooh.
double the number of colors and maybe it's okay?
I feel like it's tricky because the colorings we're defining with these regional things, they're quite specific. So if I had a list that didn't allow me to do this and make the colors disjoint, then I would run into problems very quickly.
But if your palette is
If my palette is
big,
huge, then
still finite.
sure,
Yeah.
then maybe. Yeah. I think that could be interesting, but it could be very hard.
Any other questions? If not, let's thank the speaker.